Welcome to lesson 42, Nuclear Stability and Radius. Here's the plan for today. Here is the most useful graph in nuclear physics. Neutron number running up the side, proton number along the bottom, with a band of stable nuclei running through the middle. Why does this band exist at all? Because neutrons act as the buffer. Protons repel each other electromagnetically and would blast the nucleus apart, so you need neutrons in between, adding strong force attraction without adding any repulsion. At the bottom, for light nuclei, 1 neutron per 1 proton does the job, so the band follows the line y equals x. But as you add more protons, every proton repels every other one, so the repulsion grows faster than the number of protons. You need proportionally more and more neutrons to hold it together, so the band bends upward away from the diagonal. Now the graph earns its keep. Suppose a nucleus sits above the band. What does it have too many of? Neutrons. So it needs to turn a neutron into a proton, and that's beta minus decay. It moves down and to the right towards the band. And below the band has too many protons, so it turns a proton into a neutron, beta plus decay, moving up and to the left. Every unstable nucleus is trying to get to that band, and its position tells exactly which decay it will take to get there. It's worth drawing a little 3x3 patch of the graph and plotting each decay as a move. Alpha throws out a helium nucleus, 2 protons and 2 neutrons, so it moves you down 2 and left 2. Beta minus turns a neutron into a proton, so down 1, right 1. Beta plus does the reverse, up 1, left 1. And gamma doesn't appear on this graph at all, because it changes neither the neutron number nor the proton number. It just sheds excess energy and calms a shaky nucleus down. Here's a question worth thinking hard about. Look at alpha decay on that graph, down 2, left 2. That's a move parallel to the diagonal, so at first glance it doesn't take you towards the band at all. Why would a nucleus bother doing that? The answer is that it only pays off for heavy nuclei. Up at the top of the graph, the band has bent so far away from the diagonal, it's so steep that the nucleus is so bloated with protons that the real problem isn't the ratio, it's the sheer size. So the nucleus dumps a big chunk of mass all at once. Compare that to beta decay, which sheds about only 1 in 2,000th of an atom's mass, a rounding error. Alpha is how a heavy nucleus actually slims down. And a practical warning, exam questions often chain several decays together. Track your starting and finishing N and Z carefully, step by step, and don't try to do it in your head. After a decay that changes the proton number, the new nucleus is often left in an excited state, jangling with excess energy, and it settles down by emitting a gamma photon. If you draw the nuclear energy levels, you'll often find several different pathways down, which is why a source can emit gammas at several distinct energies. Usually that happens instantly, but some excited states hang around for a long time, and those are called metastable. Stable, but only in the sense that it stays that way while we keep it that way. Technetium-99m is the famous one. The M is literally for metastable, and it's the workhorse gamma source of medical imaging, precisely because it emits clean gamma rays and lasts just long enough to be useful. So how big is a nucleus? One method uses an idea all the way back from lesson 5, electron diffraction. Fire electrons at a foil, their de Broglie wavelength, and remember, that isn't a literal wave, it's just how they behave, can be tuned by their speed. Get it to roughly the same order of magnitude as the nucleus itself, and the electrons diffract around it, producing a pattern. Measure the angle of the first minimum, and you can work back to the radius. You don't need the maths for this one, just the principle. The other method is a lovely piece of reasoning. Assume the nucleons just stack together like little balls. Then the volume of the nucleus is simply proportional to the number of nucleons A. and volume goes as r cubed. So A is proportional to r cubed, which rearranges to r equals r naught times a to the 1/3. That r naught is about 1.05 femtometers. And notice what it means. Put A equal to 1, a single nucleon, and r equals r naught. So r naught is just the radius of one nucleon. Though in truth, it varies quite a bit, because a nucleon isn't really a neat sphere. Experimentally, you take logs. Plot the natural log of r against the natural log of A, and you get a straight line whose intercept is the natural log of r naught. And here is the deep consequence, which is worth pausing on. If volume is proportional to the number of nucleons, and each nucleon has essentially the same mass, then mass over volume, the density, is the same for every nucleus. Nuclear density is constant. A uranium nucleus is exactly as dense as a helium nucleus. They just have more of the same stuff. And that brings us to the end of the video. Thanks so much for watching, and check out my tutoring page below.